Okay, so make sure that you've watched the first video that I posted. That kind of goes over the basics of logarithms that we talked about yesterday, as well as some of the properties that we're gonna, we're really working on today. The three big ones that you talked about were your log addition, subtraction, and your power rules. And so just to quickly go over those, the basic idea here is if we have something like log base b of a plus log base b of b, that rule says that we can combine those into log base b of a times b. And so that turns addition here, addition of your logarithms, into multiplication, or more importantly, it turns a multiplication problem here back into addition problem. We have a similar rule with subtraction, log base b of a minus log base b of b. That's going to turn it into a subtraction problem. The big thing here, there's only one logarithm. It's log base b of a divided by b. Their order really does matter. And then our last one, and this is probably the most useful one, is if I have log base b of a to the b, what that can turn into is it says I can bring that exponent down and turn it into a multiple, b times log base b of a. That's really the one we're going to use a lot. That's one of the really more powerful things about logarithms that we're going to use. And so you'll see that one used in a couple of these other examples that we're going to do. So the first thing I want to talk about that wasn't mentioned in that first video was the change of base formula. And the first thing I want to do is just show you where this thing comes from. This one's a pretty easy one to show. And then we'll use an example here of why we might want to use that. But just know that when we're actually solving logarithms, usually we won't use this. And so the change of base formula says that if we have a log base x of y, so some base x, we can change it to a different base, so say base b, just by using this formula. Log base x of y is going to be log base b of y over log base b of x. The old base goes in the bottom, and we have our new base. Now it seems like we might not want to use that, but a lot of times that's going to help us change into a base either that our calculator can use, or maybe a base that's going to be a little bit easier to do without a calculator. And so, just to go ahead and kind of show you why this works, and also a little bit of why we don't usually need it, let's just start with this left-hand side. And so if we have log base x of y, we'll just say that equals z. Now to start working on this, what we're going to do is just rewrite this into our exponential form. So x is our base, to the z equals y. Now, we can use a different base of logarithm to start to work with this along with our properties. So we're just going to pick base b again. It doesn't matter what base we use. Usually we're going to switch this into some base that we can use with our calculator. And so I'm going to take log base b of that side. And what that means, let me go ahead and see if I can just, we're going to move this over. So get rid of that. Let me just move over so I have some space. So I've taken log base b of this side, and then I'm going to have to take log base b of that side. I'm allowed to do that because I'm just taking the exact same log on both sides. It just happened to be a different log than I had originally. Now we use our properties of logarithms here to say that this z can move down and become a multiple. So now I have z times log base b of x is equal to log base b of y. And now I can just get that z by itself by dividing by log base b of x and dividing by log base b of x. And so you'll see here, z, which was originally log base x of y, is equal to log base b of y over log base b of x. That's going to be a really, really good one to know. It's going to come up quite a bit in a lot of these problems that we're going to do. Now let's just take a quick look at why we might want to use that. So let's just say I have something like log base 7 of 5. That's not something we can deal with. Most of your calculators don't have a log base 7, and it's not going to be a nice logarithm to come up with without a calculator. And so the reason we're going to change this is our change of base formula allows us to change this into one of two bases. We can either change it into a common logarithm, which is base 10, or we can change it into a natural logarithm. Natural. And so in the common logarithm, that's just going to look like log of 5 over log of 7. And remember, those are base 10s. We just don't write the base 10. That could be evaluated on a calculator very easily. Or with natural logarithms, natural log of 5 over natural log of 7. And again, that can be evaluated on a calculator very, very easily. Either one is fine. They both give you the same answer. Next up, that first video showed you an example of expanding logarithms. You can also use these properties the other way around to combine logarithms. And so really the important thing here is we have these are all the same base. And so the first thing I'm going to do is use our exponent rule to go ahead and put these exponents back up on top. And so here we're going to have log base 6 of x squared minus log base 6 of y plus log base 6 of z to the third. Now I can go through and start one at a time combining these logarithms. Here, I've got two logarithms that are subtracted. And so that's going to let me combine these as one logarithm, log base 6. And now I'm going to have x squared over y. It's going to turn it into a division problem. And then I've still got plus log base 6 of z to the third. And then finally, since I'm adding these logarithms, that's going to turn into a multiplication problem. And so keep in mind that's z over 1 right now, so when I multiply these, I'd multiply x squared times z to the third on the top, y times 1 on the bottom. And so when I combine these, I'd have log base 6 of x squared, z to the third, divided by y. So depending on what I want to do, sometimes combining the logarithms into one is going to be useful. We'll see that when we start solving equations. Sometimes splitting them up is useful, and you'll see some of those in your homework too. The last thing is just a couple of examples like what you'll see in your homework. You'll have to combine and you'll have to expand logarithms, but let's just take a look at using some of these properties to help us evaluate logarithms. So here we have log of 50 plus log of 20. Neither one of those are very simple to deal with on their own, but using our property of the multiplication rule, log of 50 plus log of 20 is going to equal log and 50 times 20. Well, that is going to be, 50 times 20, that is going to be 1,000. And so we're dealing with log of 1,000. Now, remember this is base 10, so log base 10 of 1,000. We're asking the question, 10 to the what power is equal to 1,000? And when we put it that way, log base 10 of 1,000 is equal to 3. It's much easier to evaluate than it is in this form, where log base 10 of 50 is not something that's very easy to deal with. Next up, something like this, log base 5 of 25 to the 7. Again, not so easy to deal with here, but if we remember our exponent rule to turn that into multiplication, we actually have 7 times log base 5 of 25. And now this part's actually a lot easier to deal with. Log base 5 of 25, if you remember, is saying 5 to the what power equals 25. And so this part right here is just 2. And so here we have 7 times 2, and that is 14. So by bringing that exponent down, we're able to make that problem a little bit easier to deal with. This final example here is an example of those inverse properties of logarithms. And so here we see we have natural log of e to the something. And anytime we see that natural log of e, since natural log is log base e, those are inverses. And in this case, now once I do that, I now have natural log of e to the fourth left over. And again, since natural log of e, those are inverses, that whole thing just evaluates to 4. This is going to be something you're going to see quite a bit, using natural logs to remove exponents. And so you hopefully saw those last few examples in the first video. That's actually going to come up more later on. But for now, you'll just see those simplifying expressions help you out in solving or evaluating for different logarithms.